In this video, we're going to do the constructed response problem at the bottom of page 618 in our workbook. So let's take a look at what we've got here. All right, so let's consider the differential equation dy dx is equal to x over y to answer the following questions. A, on the axes below, sketch a slope field for the equation. All right, so what we want to do is for each one of these xy points, we want to calculate x over y and then draw a little tick mark that's got that slope to it. All right, so give that a shot yourself. All right, so here's how I would go about it. We can just kind of go through and tackle as many different cases as we can. So first of all, when x and y are both 0, which is at the origin, then this is 0 over 0, which doesn't exist at all. So we can't have a slope field point put in for the origin, and that's okay. Otherwise, if x is equal to 0 and y isn't equal to 0, all right, so that's all of these points here, then the slope is going to be 0. All right, so I'll draw all right. Same thing, let's deal with the x-axis though. So here's where the x is not equal to 0, but y is. So here we're dividing a non-zero number by 0, and that's going to be kind of infinite. I want to kind of use wavy language when I do that. But as far as slopes go, it's going to be a vertical slope. All right, so we're looking something like that. What happens when x is equal to y, but not equal to 0? Then the slope is going to be positive 1. All right, and what are those points on this grid? So those are points kind of like right along here. All right, let's deal with the other diagonal. So this is where x and y are the same magnitude but different signs. All right, so we've got like 1, -1. If x is 1 and y equals -1, then this quotient is -1. And kind of picking up the pattern here. All right, so what happens when x is 1 and y is 2? When x is 1 and y is 2, then this is a slope of 1/2. So 1/2, it's going to be a positive slope, but it's going to be kind of gentle. All right, this is going to be a slope of 1/3. So this is going to be a little bit more gentle yet. Over here, we're going to have a slope of 2/3, which is going to be, again, not as steep as 1, but more gentle than these. When x is 2 and y is 1, then this is going to be a slope of 2, which is going to be kind of steep. All right, same thing is going to happen on the negative side, where both of these, where both x and y are negative, they're also going to cancel each other out, and we're going to wind up with positive slopes. So we're going to have, and it's going to be very steep right here, and a little bit more gentle over here. All right, and the same thing in the second and fourth quadrant. It's going to be the same, except that these slopes are going to be negative because these are different signs. So they're not going to cancel each other out. All right, so, well, once again, these are getting more and more gentle. This is pretty steep. This is pretty gentle. You can see that I am not losing much sleep over how precise or not precise I am. But this is the kind of thing that is demonstrating an understanding of the way it looks. And so you can see we kind of have interesting shapes here. All right, so B is to sketch a solution curve that passes through the point 0, -1 on your slope field. So 0, -1 is right here. Maybe why don't I use my Sharpie for this? Okay, so here the slope is going to be 0. And you can see that it's kind of tailing off here. maybe, yeah, maybe not quite that much. All right, so something maybe a little bit more like this than like that. But that's kind of, you're getting the sense, you're going with the flow that's here. And part C is to find the particular solution to this differential equation where f of 0 is equal to -1. So we want to find the exact formula for this curve right here. All right, so this is something we did a couple modules ago. How can we find a solution, the family of solutions that satisfies this equation? Whoops, x over y. That's my mistake. All right, so the first thing we'll do is we can cross multiply to separate the variables. So we've got y dy is equal to x dx. And now we can find the indefinite integral of each of these equations. All right, and so that's going to be 1/2 y squared is equal to 1/2 x squared plus some constant. And why don't we multiply through by 2 just to clear that out? So we've got y squared is equal to x squared plus c. That's a little bit ugly, multiplying c by 2 and still getting c. I think that's fine though, honestly, because this is just any old constant. Any old real constant times 2 is just any old real constant. This is a little bit of abuse of the notation. Maybe I should put 1/2 there just to feel really good about it. But I'm not losing any sleep over it. All right, so this is not the particular solution. This is the family of solutions that satisfy this differential equation. So let's put in our initial condition. All right, so we've got x equals 0 and y equals -1. So -1 squared is equal to 0 squared plus c. -1 squared is 1 is equal to c. All right, so what we have is y squared is equal to x squared plus 1. Is that my final answer? Should I toss a box around there? Honestly, I'd lose a point if I did that because they're asking for the solution y is equal to f of x, and I've got y squared here. All right, so I'm going to do something to get y here alone. I'm just going to take the square root of both sides of the equation, x squared plus 1. All right, and now I'll put a box around this and claim victory, right? You might know me well enough to know that every time I say that, the answer is no. Why is this not the equation of this curve? What's something that's really obvious about this curve that is not reflected in this function? This is a negative function. All of these values are negative values, and the square root is always a positive number. All right, so what we need to respect here is when we're taking the square root of both sides, y is actually equal to, it could be either the positive or negative value of this function. All right, and so the positive or negative values of this function, let me give you a sense. The other function, this is the negative side. The positive side would look something like, I've got a fresh chance to kind of make this better. Yeah, that wasn't remarkable. Well, it was okay. So this is y is equal to the square root of x squared plus 1. And this function down here is y is equal to negative the square root of x squared plus 1. All right, both of them put together are the solution set of this function right here, and that's called, if you took a class in pre-calculus and learned about conic sections, you might recognize this shape is a hyperbola. This is a much better arc of a hyperbola than this is now that I look at it. But the branch that they want us to look at, since they've got f of 0 is equal to -1, is equal to negative x squared plus 1. So this is what we're going to put our box around and claim victory and get an escape before my gel pen gets any more out of ink. All right, so there's a lot going on there, but let's just recap what we did. So we drew a slope field. We sketched the solution for 0, -1. And then we solved a differential equation where we separated the variables and then took the indefinite integral of both sides and then figured out the equation of the individual branch that's got the point that we were interested in. All right, so there was a lot going on there. A lot of opportunities to get 8 out of 9 points or 7 out of 9 points. But when you're faced with a question like that, you definitely want to get those 7 points that you can get, even if there are a couple traps that might keep you from getting those last 2 points. So understanding slope fields is going to help you when it comes to tackling questions like this.